Good morning, good afternoon, everyone, depending on where you are. We are on our third day of Generator Interconnection workshop. My name is Julia Matevosyan. I'm a Chief Engineer at Energy Systems Integration Group. In this workshop, we have NAGF, NERC, and EPRI as our partners. This is the third day. As I mentioned, the first day we focused on interconnection process. Yesterday we focused on studies and modeling. And today we focus on interconnection requirements and specifically at IEEE2800 standard. And also we'll talk about DOE's initiative I2X. And then we'll close the workshop with some highlights of what we heard throughout those 3 days. So just a reminder to use slido.com for your questions. And today's code is ESIG 11. So you can just go there, post your questions, and also vote up the questions that have already been asked if you like them. And this allows us to sort through the questions and prioritize better. Without any further ado, let's go ahead and get started. If you noticed, we have an introduction to each of the days, and today's introduction will be delivered by Jason McDowell from Ieee Energy Consulting. Jason, the floor is yours.
Thank you, Julia. Hi, everyone. Good day and welcome. It's really great to be part of this workshop and see so much of great dialogue that's been happening over the last couple of days. I'd like to kick today off by really generally talking about the need for harmonization around interconnection requirements and processes when it comes to interconnecting all of the resources that we've been talking about over the last couple of days. I would like to really also have an opportunity to give an example for harmonization, in addition to generally talking about harmonization of requirements, and hopefully that will kick off a lot more depth in discussion in the two panels that we have planned for today. So, I'd like to start off generally by acknowledging something we already all know. And the fact is that there's so much change happening that's driven a lot by either policy or needs of system operators and equipment owners to continue supporting the grid from a technology point of view, continue supporting the grid from a reliability point of view, but understanding that as the generation mix is changing and as the technology is changing, the requirements also need to change, and the requirements and capabilities of the equipment to meet system needs is also evolving. And for those of you that have been tuned in to a lot of our ESIG webinars and workshops, you'll recognize a lot of this slide anyway that Julie and I frequently refer to, but it's so very true. And I want to reiterate how important it is for all the collaboration to happen between all the different stakeholders to define requirements based on evolving system needs and based on evolving technology. So today, since we're talking about interconnection requirements, really want to point to concepts we've heard from many ESIG presentations, as well as NERC, as well as IEEE, many discussions that we've had in many forums around grid code evolution and standards evolution as well. And that is a balance is needed between for requirements and processes between making sure that they are defined well enough to understand what the system needs are and unlock the full capability of equipment and performance on the grid, but not be too vague that in a way that would risk performance and reliability, but also not be too prescriptive and too constraining to be prohibitive for integration and have prohibitive integration complexity, right? So it's this balance and harmonization that needs to happen, and recognizing that different areas are in different levels of maturity in terms of where the penetration is, how those areas work together. So really it's necessary to balance several elements for future grid needs, and harmonized grid codes, harmonized interconnection requirements, harmonized processes play a very critical role in the development of those technology capabilities to meet the grid needs. That includes what tools do we need to use, what models do we need to use to identify those risks and phenomenon, have harmonized interconnection and integrated planning practices that fully identify those risks and understand how to mitigate them. Focus on interoperability between equipment and between controls. Support the grid for inertia, support grid voltage and frequency, as well as equipment control stability as we integrate more inverter-based resources and make the most out of those resources as the mix changes. And obviously, we've all heard over the last couple of days that the benefit and the need of having collaboration between regulators, system operators, equipment owners, and OEMs is certainly a very important piece of keeping that balance in place and making sure requirements are harmonized. So I'd like to also talk some more in detail about the fact that, some areas have some requirements, other areas may have different requirements. Some areas adopt strictly from the LGIA, LGIP, and the NERC requirements, and that serves them well for the needs that they have with their penetration levels today. Other areas have more advanced requirements that continue to evolve and are different from one system operator to the other, perhaps because there is a higher penetration in those areas that need more definition of the capabilities, the modeling, and the performance. But the one thing that from an OEM perspective, and also just looking at how to integrate all of this together, many different requirements are also somewhat difficult to manage from a wholesale interconnection point of view, because with different requirements in different areas that may not be harmonized, it can add complexity, it adds cost, it adds time to be able to assess the different areas. And there's obviously benefit to taking the best balanced capabilities, the best balanced performance needs and performance requirements, and allow them to be proliferated in many different areas, so it's much easier to scale those capabilities across multiple areas. This is being done in various areas around the world right now. One example is NSOE. The requirements for generators have that coordination that's happened across all the European TSOs and entities. So what's happening right now with IEEE2800. We're certainly undergoing a lot of discussion based on IEEE2800 today. How does it get deployed? In what form does it get deployed? How do we test and measure through new standards like IEEE2800.2? All of those things are still very much being discussed as we're going to hear more about later today. And even I want to really call out and have a shout out to NERC IRPS reliability guidelines as well. There's a lot of emphasis and effort from the industry that has gone into that. Really want to thank Ryan and Julia and many others on this call that have been involved and engaged with that very fruitful discussion and creation of the reliability guidelines. So harmonization and balanced requirements is needed for efficient and cost-effective deployment of capabilities across multiple areas in order to really scale the transformation that we're going through today. So wanted to also offer maybe a humble opportunity to give some feedback on an area where there's an opportunity for harmonization, and maybe give some feedback on some of the language in the FERC NOPR and the IEEE2800 standards and the NERC standards. So one of the clauses I picked out here was from the clause 973, the ride-through capability and performance. And this clause basically says that for a system disturbance, for abnormal frequency and voltage, that the facility must maintain real power production at pre-disturbance levels unless providing PFR or FFR. It must provide dynamic reactive power support to maintain system voltage in accordance with the generating facility's voltage schedule. So wanted to just pull on a couple of these in terms of harmonization of language of some of the other requirements. One of the things I think is challenging with calling out the reactive power to be left at pre-disturbance levels. I think the intent of that was certainly to avoid what we all know has been happening in certain disturbances that happened since 2016 around the U.S. and California and more recently in Texas, called momentary cessation, where there is a a blocking or a total reduction of total current into the grid upon a fault. I think harmonizing that language with the other standards is good, because the challenge with calling out the active power and reactive power performance is that under normal conditions that I'm showing here on the left, when there's a voltage disturbance, when there's an electrical fault, and when the voltage is reduced, it's a very important and good behavior for the grid, and a necessary behavior for the grid, for that active power to be reduced during the fault. And the reason is we want to make sure that we don't push too much active power across the network into a voltage that's already depressed, into a voltage that's not healthy. Otherwise, we're going to further collapse the voltage. We're going to further cause reliability risk, and could also cause more cascading outages. So as the fault is happening, as you can see here, the voltage is depressed, active power is reduced, reactive power is prioritized so that we can boost the voltage, and the inverter-based equipment can ride through the event as is needed by that stabilizing reactive power, reactive current injection. And then as soon as that fault clears, then the active power will recover, but only after the voltage recovers. We don't want to push watts through an unhealthy voltage or a voltage that hasn't fully recovered. So that's one of the things that I wanted to point out. And there's opportunity to harmonize with some of the language in PRC 24 and IEEE 2800 that I'll share in a minute. The other aspect is maintaining facility voltage, maintaining a voltage schedule. I think that's certainly something that obviously in the steady state or quasi-steady state we want to do. And that certainly holds true before a disturbance and after a disturbance. During a disturbance, however, the terminal voltage of the plant, and particularly of the inverter-based resources, is managed by the inverter-based resource controls itself. So during the voltage depression, during the fault event, the inverters will do what they need to do to inject reactive current. They have very fast controls that operate in the order of milliseconds. I have a call out here of a total quickly responding to an event within 100 milliseconds. That's debatable. Is it total response? Is it settling time? That's not the point I'm trying to make. The point I'm trying to make is that it's fast, much faster than the plant level control is, to keep the voltage constant and stable and regulated at the point of connection with the plant level control. The plant level controls will take over and regulate the quasi-steady state at the point of connection on the order of seconds to tens of seconds due to normal fluctuations of the grid. But during disturbances, the behavior in the very short amount of time during and just after the disturbance is dominated by the inverter-based resource control. So I think one thing that could be good to consider is that during the disturbance, instead of necessarily only calling out what the plant voltage is doing, making sure the inverter-based resource adequately manages its own reactive current, adequately manages its own terminal quantities in order to ride through. And then eventually when the fault clears, we can make sure to recover the voltage as is needed through coordinated hierarchical control at the plant level. So just some considerations I'd like to leave to and options, for harmonization of the language before we break here and go to the next session. There's some language called out specifically in the latest version of PRC 24. Requirement 1 says each generator owner shall set as applicable frequency protection in accordance with PRC 24 attachment 1 so that it does not cause the generating resource to trip or cease injecting current within the no trip zone. I would love to hear comments, and please correct me if I'm wrong, if I got the intent of the FERC-NOPR wrong. But I think this, if it is intended to look at preventing momentary cessation during, the period when the voltage or the frequency is within the curves of PRC 24, the language of cease injecting current is probably more relevant than calling out active power to be maintained based on pre-fault levels. Also, IEEE 2800 has some language in here too that could be helpful for coordination. It does acknowledge that the active power recovery time shall be configurable within 1 to 10 seconds, and that acknowledges that the active power will reduce or deviate during a fault. And then recover after that fault is cleared. And also the language acknowledges that in very weak grids, that to reduce any oscillatory behavior or any control interactions that may happen, it's desirable to reduce the average rate of power recovery. That would help eliminate or at least reduce the risk of those oscillations happening. And that needs to be done in consultation with the transmission system owner. It also acknowledges that there's a couple of different priorities, active power priority and reactive power priority, that have to be demonstrated. And by default, the IBR should operate as a reactive power priority mode for both low and high voltage disturbance events. And then if for any reason active power priority is needed, that would be coordinated with the transmission system owner operator. But by and large, for the vast majority of systems around the world that need to have the reactive power support and the voltage support both during and after an event, reactive power priority is a very preferred and very effective means for riding through recovering faults and making sure that we can support localized voltage and avoid interactions. So just some food for thought and food for feedback. I think we'll hear a lot more from many of the panelists today and looking forward to it. So with that, I'd like to wrap up. If you have any questions, maybe we can entertain those at the end of the next session. And that concludes my presentation now. I'd like to now hand it over to Manish Patel, who will kick us off for the initial panel. Thank you, Manish. Please take it away.
All right. Thank you, Jason. So great thoughts there, Jason. Appreciate it. So to folks listening in, thanks for joining today. Just want to mention a couple of things quickly. We are taking questions on slido.com. So please, if you have any questions for Jason, go ahead and post them on slido.com. The code for today is ESIG 11, ESIG 11. And we'll try to address as many questions as possible towards the end of this session, but before we break, take a short break. All right, with that said, welcome. This is the IEEE 2800 section. I'm Manish Patel. I used to be a vice chair of IEEE 2800. Nowadays, I joke, my middle name is IEEE 2800. I'm with Southern Company, been here almost 16 years now. Looking forward to chatting with some of the folks here listed on the slide. So very first, let's have a little bit of overview of what is IEEE 2800 and then roadmap to adoption of IEEE 2800. Andy Hoke is here to share some thoughts on those. He's a principal engineer with NREL. With that, Andy, the stage is yours.
Very good. Thanks, Manish. Let me get back to the beginning of the slides here. Yeah, so as Manish said, I'm going to share a brief overview of IEEE 2800. We could talk about it for hours and hours. It's a 100-page document, not including appendices. Has lots of detailed interconnection requirements that were developed through consensus. So I'm going to give a very brief overview of that, as well as some thoughts on how we get from the standard, which was just recently published, to actually adopting the standard and getting it deployed in industry so that we can actually get some benefits out of it. I guess initially, I also want to make sure that it's clear that I'm not talking on behalf of IEEE here, nor on behalf of NREL or DOE, but rather sharing my own thoughts. So that's what's on these disclaimers. Jump right over those.
You're not sharing your slides.
Yes, go ahead.
Andy, will you share your screen, please?
Yes.
Sorry about that. Yes, here we go. Apologies for that. Okay. Yep, thanks for pointing that out. So, yeah, as I mentioned, I'm sharing my own thoughts on this, not necessarily IEEE or DOE's official thoughts. I think this slide has been fairly well throughout the workshop, but I'll just give the general overview. As we go into this new future with lots of wind and solar on the grid, we're going to need to continue to interconnect wind and solar very rapidly. And to meet national goals, we're expected to need to interconnect so much wind and solar that within, say, 10 or 20 years, there will be times of the year in all three major US interconnections where the instantaneous power coming from IBRs is in the 75 to 80 to even 90% range in terms of instantaneous generation, which means we need those IBRs to not just remain online, but to contribute to the system recovery and reliability. And so that's the main motivation between IEEE2800 is to define the basic requirements we need from those devices to get the IBRs performing the way that we need to do to get a reliable grid. Okay, so basically on a really high level, what's in IEEE2800? It attempts to harmonize interconnection requirements for all inverter-based resources that include solar, wind, storage, even HVDC if it's interconnecting, say, an offshore wind plant, and anything else connected by a power electronics device effectively. It also includes both type 3 and type 4 wind, so it's fairly comprehensive in terms of what types of inverter-based resources it includes. It was developed by a large working group, 175 different people spanning many different stakeholder groups from utilities to system operators, transmission planners, equipment manufacturers over a 2-year process, which is actually relatively fast for an IEEE standard. And it recently passed the ballot towards the end of last year with a very large ballot group of over 400 people and response rates and approval rates of over 90%, which all are very high compared to other IEEE standards that have been developed recently. So in other words, it's the result of a lot of work to develop consensus between a large number of stakeholders spanning many different groups. It was coincidentally published on Earth Day of this year. So it's now actually available online. If you have a subscription, you can usually get it for free, or if your organization doesn't have a subscription, it costs a couple $100 to get a copy of it, but it's available to the general public. Okay, a little bit more on the motivation for it. Right now, we have lots of different requirements across different jurisdictions that have been discussed throughout this workshop, which requires more time and effort on the part of all the parties, the developers, the OEMs, and the utilities, as well as their regulators to deal with this sort of diversity of different requirements. And we're starting to realize that the grid is changing as we change from a grid that's typically based on synchronous generators to one that is more and more based upon inverter-based resources. And those resources have different capabilities. Sometimes they may have better capabilities. Sometimes their capabilities may have weaknesses relative to synchronous generators. And so we need to change the interconnection requirements to account for those different requirements. And of course, the requirements across different regions and across different technologies are not always balanced. And so IEEE2800 tries to unify that across all the different transmission operators. Of course, it's an IEEE standard is 100% voluntary. It doesn't have any effect until the recognizant entity adopts it. So that's the part where we are in the process right now, is reaching out to entities that govern interconnection requirements and figuring out, would it make sense for some of those entities to adopt this standard. A little bit more on the diversity of the working group. On this slide, I won't go into the details, but you can see it was sponsored by many different groups within IEEE and outside of IEEE, and included transmission operators, service providers, consultants, government bodies, producers of equipment, users of equipment, including IBR developers. So many different people across the spectrum of industry, including probably many of the people that are online today, were involved in developing this standard. So we think it represents a good cross-section of industry and is a strong consensus. Among the working group, it had a 99% approval rate at the end of those 2 years. Okay, so where does IEEE2800 fit in the North American interconnection standards landscape? So we have had for quite some time IEEE 1547. It was recently updated. Well, not that all that recently now anyway, in 2018. It applies to distribution connected resources, potentially some radial subtransmission connected resources as well, but is definitely not designed to apply to transmission connected or meshed subtransmission connected resources. In fact, its application in those environments has been maybe partly at fault for some of the different reliability events that have been occurring around the country recently. And so IEEE 2800 attempts to fill that gap by creating the first national interconnection performance standard for inverter-based resources connected to transmission and subtransmission. On the compliance verification side, in 1547, we have a corresponding standard called 1547.1 that contains the test procedures to know whether an inverter-based resource or anything connected to distribution complies with 1547. We're currently developing a standard called IEEE 2800.2, which would serve a similar purpose for these transmission connected resources. It's going to take a couple years to develop, and we'll talk about how that plays into the adoption process for 2800 later. But as I mentioned earlier, none of these standards are mandatory when published by IEEE. They only become applicable, and we only see any benefit out of them once they're adopted by the entities that are in charge of interconnection requirements. So right now, 1547 is going through this process of being adopted by distribution operators and their regulators. And then we're kicking off the same process for IEEE 2800 right now. A little bit of background information on IEEE standards. Many of you might be familiar with this. IEEE creates standards, recommended practices, and guides. 2800, like 1547, is a standard, which means it uses shell language. In other words, it puts out requirements for actual interconnection of IBRs. This is in contrast to recommended practices, which use should language, and then guides, which are things like application guides and use may language. Okay, so what do we expect from IEEE 800? What kind of value do we expect to get from it? I mentioned that we get hopefully widely accepted unified technical minimum requirements for inverter-based resources, and we hope that that will speed up the interconnection of those resources. We hope that the standard was designed to provide those requirements, but provide them so that you comply at the point of measurement of the plant, rather than looking inside the plant and telling you what the plant needs to look like on the inside. So in other words, it's not an equipment design standard or a plant design standard. It provides the flexibility for a developer to design a plant however they want, as long as they meet the basic requirements of interconnection of IEEE 2800. This is the same philosophy followed in 1547 that has been successful for many years. IEEE 2800 specifies functional capabilities, meaning it will say you have to be capable of riding through a certain type of event, or you have to be capable of providing a certain type of voltage regulation response, but it won't specify the utilization of those responses. The utilization of those responses is left up to markets or system operators to decide. And so basically it just decides what the plant needs to be capable of, but not how that capability needs to be used. For each of those capabilities, it provides different ranges of functional default settings and ranges of adjustability within those settings. It also specifies, once the plant is interconnected, what sort of monitoring needs to be placed on the plant. Do we need a digital fault recorder? Do we need a PMU, et cetera? Provides specific requirements on those types of settings for plants, which is shown to be crucial for diagnosis of events that have happened in the field. It also provides some information on data needed to validate that models of the plants are valid. It also provides an outline of a process for verification of the requirements that it outlines, but it doesn't provide the detailed procedures for those verification steps. That would occur in IEEE 2800.2. I mentioned earlier that it covers all transmission and subtransmission connected wind, solar, battery, and HVDC voltage source converters. And then there's a few things that we don't necessarily expect to get from IEEE2800. It's not going to go into detail about what to expect from grid forming inverter-based resources, even though those have been sort of a hot topic recently. It does apply to any type of IBR, including a grid forming inverter-based resource. It's also not going to define an interconnection process, right? So it's not going to solve all the problems that we've been talking about in this workshop. It's just going to provide some basic requirements that could be used in such a process to hopefully make the process more standardized and more smooth for everybody. I mentioned earlier, it doesn't necessarily provide the procedures to verify that an inverter-based resource complies with its requirements. Those are currently being developed. And on the behalf of the 2800 leadership team and the 2800.2 leadership team, it's important to note that we don't see the development of the 2800.2 verification procedures as a necessary step to start applying IEEE 2800. IEEE 2800 could be applied as soon as an entity is ready based on existing verification methods that are already being used in industry.
Yeah. Hey, Andy, this is Manish. Sorry to interject here, but if you can wrap up in maybe 2-3 minutes.
Okay, sounds good. I talked about capability versus utilization, so I'll skip that. This slide just talks about some of the details that are in IEEE 2800. What are we going to find in there? I'll let folks read that offline because there's a lot in there, but you can basically see that it includes things from reactive power control, power quality, ride through, frequency response, etc. It includes details on voltage and reactive power control modes. I'm going to go through that quickly. It includes details of primary frequency response and fast frequency response requirements. It includes details of ride-through requirements. Jason mentioned earlier that there's potentially some conflicts between what the language of the NOPR and the language in IEEE 2800, which should be perhaps examined. Frequency ride-through capability as well, including rate of change of frequency ride-through capability, modeling data I mentioned earlier. Again, a potential conflict there between the NOPR and IEEE 2800 that could be looked at. Okay, so what comes next? We're working on IEEE 2800.2 development. That's going to take a couple of years, but in the meantime, people can already start taking a look at IEEE 2800 adoption. There's some additional slides at the end here providing more information on 2800.2 just for your information offline to take a look at. And if you want to get involved, if you're interested in this standard, this is the activity going on right now. And we would definitely love to have any knowledgeable entities, especially OEMs, utilities, manufacturers of equipment involved. So in other words, just a quick summary slide, and I'll finish up here, Manish. This is a big standard. It's a big step the industry is trying to take. I'm not trying to say it's going to be easy. It's going to take a lot of effort across all stakeholders to make this transition to inverter-based resources. And that effort is going to be needed with or without IEEE 2800. What we're hoping is that if we can get IEEE 2800 adopted widely, then it becomes, once you get over that initial hump of getting it adopted and getting processes and technology adjusted to include these new requirements, then that actually makes the whole process easier going forward once you get over that initial hump. So that's the idea. And I think the longer one waits to adopt and make these changes, whether it's through 2800 or through some other process, the harder it gets because you get more and more diversity of resources online that maybe don't meet basic requirements. So I think that's the main messages I wanted to send. Thanks for the time to let it present, Mish, and we'll let you go ahead to the other presenters.
All right, thank you, Andy. And again, a reminder, if you have questions for Andy, please use Slido to post them, and we'll try to address them as many as possible towards the end of the session. So the next session here is a roundtable type of discussion. This is actually first time me trying to do that, and that too virtually. So I hope I'm successful. So look, folks, I'm a transmission guy. It's easy for me to write a standard and hope that the equipment is available that is compliance with that standard. But understand that there are some challenges, right? So we thought we'll talk to OEMs and maybe a plant developer and see what are their thoughts on making available equipment that is compliant with 2800. So today we have 5 individuals with us. Lucas Newbrink is a senior application engineer with SMA America. Samir Dal, he's a grid specialist with Siemens Gamesa Renewables. Alex Shatuk, lead electrical engineer with Vestas. Rajat Majumdar, he's a lead grid connection specialist with Ørsted, focused on offshore wind plants. And then last but not least, Sid Punt, he's a senior systems engineering manager with GE Power Conversion. So I'll pose this 4 questions to all those folks and see what their thoughts are. So we'll start with the first one. What are the challenges in designing an IBF plan to meet IEEE 2800 requirements? If you have seen the standard itself, you will realize that most of the requirements apply at the plant level, right? So Rajat, I'll start with you. What are your thoughts? Can we expect when some of the challenges, etc., in designing a plant that meets IEEE 2800 requirements?
Thank you so much, Manish. Hope you can hear me okay.
Yes, we hear you.
Perfect. So before I answer your question, I think I would also take a little time just highlighting a fact that, of course, there are challenges. I'm going to get into that. But before 2800 2022 was published, there was, no grid code standards per se for IBR-based plants here in US, and all OEMs and the project developer did what the best they could do, and often that ended up in some lack of consistency. Sometimes it's a moving target. An event happened, and the measures or steps were taken by the affected entities, whether it's the grid operator or transmission owner, and sometimes those steps were a little bit in a rush, created immense amount of challenge for both developer and the OEM. Sometimes those challenges came in a form of modeling, or sometimes it's a form of a performance requirement, such as the model validation at a unit level, model requirement in a new software, performance requirements such as active power recovery, reactive power capability, so on and so forth. So what I'm trying to get at, all of those are needed, but there was nothing that was creating a guidance or setting a target. So with that, when we have 2800 2022, what I would say that it has set a level playing field. Therefore, as Andy and Jason both highlighted, that it is not a design standard, but at the same time, I think that it has created a clear enough target for the design. Now it's up to different manufacturers that how are they going to accomplish those, but it's definitely, something that we can aim for. So I just wanted to give that prelude before I get into the challenge part of it, that being an integral part of the 2800 2022 development team, I think it's a big step towards getting into near 100% renewable based resources here, everywhere here in US. However, as any new standards, and getting into the challenging part, 2800 2022 has its own challenges, and even if the members of working group, various subgroup leads, and the participant in subgroups, they did their best to create a clear set of requirements with language of the standard itself, footnotes, but of course nothing is perfect. So without having a test procedure and various interpretation, it's plausible by various stakeholders. So in one hand, I do agree with Andy what he just said, that we should not wait until 2800.2 is finalized before adopting 2800, because one can of course take certain requirement of 2800 and use it with the test procedure that they have been using today, let's say PRC24, right? So that can be used. However, 28.2 is actively worked on. It will take time, and therefore that's one of the challenge, that how are we going to adopt it without having a clear precedence on the test procedure. And another thing is, even though the developer and the owner for the company I work for, we are the ultimate responsible for the compliance, and the developer owner will play a vital role in designing the balance of plant, any other equipment at the substation level. However, support from the OEMs of IBRs, whether it's wind turbine generators, solar manufacturer, energy storage, those are of immense importance. And therefore, what we are doing as a developer to overcome these challenges, that we are trying to work in a very collaborative manner with our OEM partners, try to identifying the gaps and find out that how we can work in harmony to achieve it. But it's not a smooth sailing process. It has its challenges. One of the biggest thing is the timeline. At this stage, we cannot really comment that when, let's say, Ørsted is going to be able to design a plant which is going to be completely 2800 compliant, because it depends on many different factors, including our OEM partners. So, with that, what I would say finally, that I think we should try adopting 2800, but at the same note, let's not rush it just in order to have something. So let's try to do the best we can possibly do. And with that, I'll hand it over to you, Manish.
Thank you, Rajat. So what I hear is it's the 2800 was a right step, or a step in the right direction.
Absolutely.
And in absence of DOT 2, which would have test procedures, it may be challenging a little bit for some requirements, if not all. Understood. And obviously, from a developer's perspective, you're really dependent on OEM to provide you an equipment that can help plant meet the 2800 requirements. Thank you, Rajat, for sharing those thoughts. So then, obviously, the next question is to OEMs, right? Even though the plant, most requirements in 2800 are plant level requirements, we all know that the equipment has to be capable to support those plant level requirements. So let's go to the next question then. What are some of the hurdles with designing and then self-certifying, right? Because the DOT 2 is still being worked on. Equipment that can help plant meet IEEE 2800 requirements. We have limited time, so let's try to be as precise as possible in our responses. Let's try to hit the most important points up front. So I'll start with Samir. Samir, your thoughts?
Yeah, thank you, Manish. I would like to second Rajat's comment there. Without a proper guidance from 2800-2, it will be really challenging for OEM to, self-certify, as you put it. Self-certify to what standard, to what performance level. I also want to reiterate the fact that, most of the requirement that 2800 has is most of the OEM can already meet those requirement, right? Performance requirement. There are some that are more challenging than the rest. There are also some requirements that are so ambiguous in terms of self-certifying that can have a infinite possibility of testing and also saying like, okay, we can meet it. So without a proper guidance, I think it is going to be really challenging to say, we can certify. So I'd say, 2800-2, it is one thing to say, aim towards that, and it is completely different thing to say, I want all the equipment that are going on the field to meet these, that are two different languages and that have two different serious implications. And we'd want to avoid as much on making like the strict requirements saying you have to meet this, and without realizing there are so many other things that are going. I also wanted to kind of bring everyone's attention on the, especially on the wind turbine development cycle. It is 4 years, multi-year cycle, and I think it's true for solar inverter and battery inverter as well. 4 years development cycle, design starts 4 years from the turbine that comes to market. Turbine gets sold at least 2 years in advance from the day they get energized, right? And also remember, there are safe harbor, so-called safe harbor equipment that were sold as early as 2016 that haven't been energized yet. So how do you go back? And I know when P2800 was written, I think this was discussed that the requirement shouldn't apply to the technology that was already on field or already sold or something like that. And when entity are adopting that, they have to be vigilant on that aspect as well.
Right, right. So that is a good point, Samir. The product development cycle is 4 years, and usually turbines are sold 2 years before they go in service, and then this safe harbor equipment that is something that was sold in 2016, maybe still not in service. Now, we tried as much as possible that I-20 requirements in 2800 are not ambiguous, but I understand your point. Without the test procedure, maybe a couple of those could be interpreted a few different ways, and more clarity might be helpful. With that, Alex, your thoughts on this?
So I mean, I'll agree with Samir. The design portion of it. Um, a lot of the products currently being designed or just recently designed, they meet many or the majority of the requirements. The big kind of logistical hurdle, not to say any of the other, I agree with all his other statements too, but the big logistical hurdle that we didn't talk about is, how do you actually do the tests, and how are you actually getting those those measurements to be used for your self certification? So, I mean, there's some things like voltage steps or frequency controller, things like that that can be done kind of in a software in the loop type setup, just running scripts and running them in a software platform. But there's other things that would have to be, done in what we call like a test bench. So basically, just connecting a PV inverter or a wind turbine to a test bench or an artificial load or a bunch of shunts or something like that, and then switching those or doing other tests to kind of get an actual measured response from those products, which is good and it's done now. The only problem is that there's a very limited number of those facilities kind of in the world, right? And those facilities, they're scheduled out pretty far to the future. So, I don't think there's any problem getting the measurements. I mean, I think they're possible. They're technically possible. It would just come down to kind of scheduling and making sure that some of the larger OEMs still have access to those things. If their larger OEMs are booking these out for years in the future, just logistically speaking, having access to those test benches or other methods for self-certifying based on measurement would be a small hurdle there.
Thank you, Alex. So then let's hear from Sid. Sid, stage is yours.
Thanks, Manish. Yeah, this is Sid Pant with G Renewable Energy. Now, as you know, G is very active in the renewable energy field across a whole bunch of plant designs or equipment for plants, which includes onshore wind, offshore wind, solar, hybrids, and storage. And we also supply HVDC equipment, and fax devices, which are supplemental IPRs. And the reason I'm saying all this is that we are really very supportive of the 2800 initiative, as has been pointed out by other OEMs. And many of our engineers contributed to 2800 and are now very active in the 2800.2 working groups. Now, having said all that, there are challenges in two areas. One are technical challenges, and the others are economic, which also could be said as techno-economic from the OEM perspective. So the technical challenge, which has been mentioned before, is 2800 applies to the full plant. And in terms of saying what are the hurdles with self-certifying equipment, the question comes up, how do you self-certify equipment to a standard which really applies to the whole plant? And yes, the concern with that is that also, if we do go through some certification, then once 28.2 comes along, we might have to, in the sort of best case, just retest the equipment, but might also have to design, because as Samir pointed out, there's ambiguity in some of these specifications. So I liked one thing Jens talked about yesterday in this presentation, where he said that before 2800.2 comes along, there might be scope for providing guidance, which could help in doing these equipment designs to allow the plant to meet 2800. Again, people have talked about, and it's true, long development cycles and test cycles, and the question about what to be done with things that are installed in the field, or worse, which are in the warehouse right now, sitting for the last 4 years and yet to be installed in the field. So that is our concern. But having said all the sort of negative and the hurdles, also Alex has pointed out and others have pointed out that a lot of these things which are in the standard are in a lot of the equipment already. So
Yes.
that's probably a good thing for the next time, for the next question as we go along. Thanks, Manish.
Right. I think that's the key point. And some of those requirements that are probably not in the equipment today, I think we discussed it many times that those are not unreasonable. Now, obviously, there is a third category, which is some stringent requirements, or maybe requirements may have some ambiguity or room for interpretation, but good deal. Thank you, Sid, for that. And last but not least, Lucas, your thoughts.
Yes, hello, this is Lucas with the SMA. So I agree with what was said so far. So we have the challenges of IEEE being a plant level standard, and we don't have the testing standard yet. And I will also, I don't know, may go to the third question already a little bit, because what our plan is really to look into IEEE2800 already starting from today. So also we joined the working group to work on the testing standard, and our plan is to be like kind of in parallel with the development of the testing standard, working out what is needed on inverter level in terms of functionality we need to be compliant to plant level on plant level, working that out. This will be done kind of like until the end of this year. And we want to use the next year to implement already what is needed in terms of hardware and software changes into our devices, to making the functionalities available, which will be, in our eyes, needed to be on to have a compliance on plant level, right? Of course, we are being with that approach a little bit ahead of time. Maybe we don't use the right testing methods yet, but as I said, we are working in parallel. Being part of the working group, I think is the best approach to work alongside this process, and being ready as fast as possible. And once the testing standard is kind of finished and published, we hopefully it doesn't need to make very many retesting procedures in order to be compliant. But until that, we are not saying that we self-certify our equipment, because it's simply said not possible due to the reason we already discussed.
Yeah, good. Thank you, Lucas. So maybe just a quick follow-up question on that, and then we'll go to the last question. I guess in the short term, is it possible, and I think this is important to a lot of transmission side of the folks who are listening to us today, is it possible in a short term that, we say, okay, here is the equipment, it can comply with following requirements of 2800, and I'm just not ready to self-certify for following ones, so that at least the communication between two sides of the fence is a little bit more clear, right? We know exactly what capability has been going in service and what might happen in future plans. And very brief answer, maybe Sid and Lucas, and then we go to the next one.
Yeah, so Manish, again, you're to some extent, you're focusing on the equipment. So really that discussion has to be between the developers and the equipment manufacturers, so that the developers can then say that they can design plants to meet 2800. And so what it's obviously saying is that there's got to be a lot of give and take, and not only give and take, but discussion, really, not give and take, which is exactly what Rajat said, that they've already started. And we're seeing that being initiated on our side as well.
Right. So then that leads into our last question, right? As we were developing 2800, we had quite a bit of participation from transmission side, engineers, operators, planners, you can think about. We had a lot of participation from OEM side, but I always felt like the entity with the checkbook, right? I don't think it's the right way to say it in a formal setup, but you heard from me before. What are some of those educational opportunities for us, right? I mean, what can we do to make sure that this is a plant level requirement, appropriate equipment, if not configured correctly, plant will not meet the requirement. So how can we, what we need to do? Do you see there's a gap? Do you see we need to close that gap? Where do we go from here? I'll start with Sid and then Lucas.
Yeah, so definitely there's opportunities because we, being in this field of doing things with big wind developers and also doing things with much smaller solar inverters, see that there is a qualitative difference in the knowledge of the transmission system and what's required between those two entities. So for example, the wind guys have been in the business for more than 20 years. They know what's required. They know their customers well. The solar ones may not be as attuned because they've been in business much shorter. So I think there's a good opportunity to, just like you're doing here, to do an outreach to developers specifically, and specifically of these solar and hybrid type of plans, to educate them about their responsibilities to meet this 2800 and why it's so important.
Right.
I'll let Lucas continue with that to give him an opportunity.
Yeah, thanks. So I also agree here. And we do have on a day-to-day basis the opportunity to educate our customers, and this is what we do, based also on our experience globally. We work a lot of in projects in Australia, and there it's already common practice to simulate and to model plant level with the equipment selected and then deployed afterwards. So with that experience, we try to really educate people and make them aware of the plant level importance and the compliance to this new standards. And at the same time, of course, being transparent about our progress according to what is needed on the functionality side of the inverter in order to help being compliant on plant level. Right? Just being alone compliant on inverter level doesn't mean we are compliant on plant level. This has to be clear and has to be communicated, and this is what we do.
Right. Thank you. So
Hey,
I think.
Sorry, Manish, can I just very quickly chime in on this educational piece from a different angle?
Yes, please go ahead.
Yeah, means of course what Sid and Lucas said, 100% agree on that, and it's not long enough that I was doing a similar thing in my role as a part of an OEM. But I would say from the educational opportunity, and I believe that those actions are already in place. This workshop itself is a really good example. I think the educational opportunity also need to come from the system operator towards the developer, because one thing is equipment manufacturer, they know they have to support, so they are doing base, they're keeping their customer base informed, but at the same time all of these requirements are going to be mandated by the grid operator, TOs, from their side. So one good example I have to say, Urcot, who has started doing such an initiative. They have a public meeting. They're identifying the gaps with 2800, and I hope the interconnecting customer who contemplating connecting to Urcot, they already got the message that, hey, Urcot is going to do this, right? And this is what they're thinking. I don't believe the same level of transparency exists in rest of the country. So what I would humbly request that if any grid operator, any ISO, any TO eventually wants to adopt it, if they also reach out to their interconnecting customer, giving a heads up that this is coming on your way, and this is our interpretation of the requirement is, So the arch is driven to the developer base from both sides. One side from the equipment manufacturer, Seed and Lucas, Samir, they all highlighted, but at the same time, from the regulatory standpoint, that they understand the importance of it.
Well said, Rajat. Well said. And I think I agree with you. So that is the reason why we have next session or next in this session, Stephen Solis from Urcot to talk about what they're doing, and Brad from New England ISO to talk about what they are doing as they ponder on adoption of IEEE 2800. So why don't we do that? Let's go to Stephen Solis's presentation. He's going to talk about 2800 versus existing interconnection requirements. They have been doing some gap analysis, have learned some things. So Stephen Solis is with Urcot, as I said. He's a principal engineer focused on improving system operations. So Stephen, I'll turn it over to you. Stage is yours.
I appreciate it. Thank you, everybody. My name is Stephen Solis. I'm a principal of system operations improvement with Urcot. I work in operations and follow up on a lot of events and different things like that happen on the system to identify corrective actions that we can take. And as previously mentioned by Ryan, we have had some events here in the Texas region, and as such, we've been focused on what can we do to prevent or mitigate the impact of some of these events? And one of those things that we have looked at was recently approved IEEE 2800 standard. Early on, we didn't think it was going to be coming fast enough, and we started looking at other options with interconnection requirements. But with it being adopted earlier this year, we see it as a good technical document that has been vetted with industry, has been vetted with OEMs. So there's a lot of collaboration and acceptance to what's identified in 2800. And what we wanted to do is look at our regional rules that we have here in the Urcot region that go beyond some of the NERC standards sometimes, and really compare versus IEEE 2800 to see perhaps where Urcot has more stringent requirements than 2800. Sometimes where we do align, and then where there's gaps, where our rules don't address certain aspects or are less stringent than what 2800 identifies. So with Urcot not really, at least in the operations side, we weren't as familiar with 2800. We did solicit some help, and we got some help with looking at this and with EPRI and taking a comprehensive look at our rules and comparing. What we're doing then is with those gaps, we're prioritizing. We're also looking at a wholesale adoption of 2800, but there are some challenges to that kind of approach, as well as a piecemeal adoption, where we're perhaps looking at a particular section and really making those enhancements to our rules to align with, or perhaps even in some instances exceed what's identified in 2800. As mentioned, we did start an inverter-based resource task force in the Urcot region. We began that at the beginning of this year, and we meet monthly, and we discuss the events. We discuss 2800. We discuss kind of what's going on in other regions, other technical conferences, try to bring that information through to Urcot. And we're hoping to foster collaboration. We're actually going to start open and closed session meetings moving forward to kind of allow more freer discussion to occur in talking about some of the issues that we are seeing in our region. So that is going along well. For those of you who may not be familiar with the Urcot stakeholder rules, we do have different groups of documents. So we have the Urcot nodal protocols, which identify a lot of rules for the Urcot region. We have operating guides too, which tend to be used a little bit more by the operators within the region. we have planning guides, and we have model quality guides as well. So IEEE 2800 came out. We wanted to do a comparison with these bodies of rules with 2800 to get a particular assessment of where we had opportunities for improvement. That preliminary gap assessment was done. EPRI helped us. Julia also participated. She used to work at Urcot. She had some knowledge to our rules as well. So when you look at what they assessed, there was 13 high-level gaps related to Urcot rules in comparison to 2800 mandatory requirements. And while we do have some language in the queue to look at wholesale adoption, that is being vetted internally. There are some challenges, as mentioned, because a lot of times, 2800-2 is going to go a little bit further, looking at some of the performance and testing side of it so that it can be more well-rounded. In our regional rules, there's a lot of push for, okay, you want to say capability, how are we going to ensure that that capability is there? At what stage are we going to do that? Which entities are responsible for what? How are we going to periodically test, or ensure performance? Those types of things have to be worked out in the rules. And so we are also drafting language right now, looking at piecemeal adoption. So for example, I put a little item 1 there. Probably first priority on our list is capability at 0 active power. VARs at night, VARs at 0 megawatt output. We see the interconnection queue. We don't see a technological barrier. In fact, the cost of enabling this is quite inexpensive to do it up front rather than perhaps waiting till later and trying to retrofit. So we want to be clear, we're moving in that direction. We're going to be requiring that. And then you see item 2, all the 2s there are probably what's coming next, where we need to look at all of our ride-through requirements. We're taking the lessons learned that we have from the Odessa events, all of those issues. We see a couple of opportunities for sure that while we have an overarching performance requirement that's good, we need to be more detailed so that the developers and those interconnecting to our system have crystal clear expectations of what they need to be able to ride through. And then we also have some opportunities on some of the frequency side that we would go after the other ride-through requirements. So we kind of looked at all the gaps that they identified, we prioritized, and now we're going through sequentially as we draft rules that we're going to introduce to our stakeholder process one by one. Sometimes they'll be in parallel, but we're just prioritizing so that we can get those rules out as quickly as possible. All of this while we are doing event analysis, while we are learning from these events. Urcot is an independent system operator. We don't claim to be a subject matter expert in inverter-based resources, but we are learning, and we're learning fast just due to the nature of what's going on in the system. So this type of gap analysis was particularly helpful in doing such prioritization. And just to give a couple of examples with the recent Odessa events, phase angle jump is one example. So in our first Odessa event, we had phase lock loop, PLL, loss of sync. We went through, identified that as an area of improvement. Several units disabled that particular feature. But then the next thing got them, which was phase angle jump in some instances. And so we had 3 plants that lost 385 megawatts due to phase angle jump trips, all with the same OEM. And the plants had all inverters trip with expected phase angle deviation greater than 15 degrees. So that's where it was set. Now, if you compare IEEE 2800, section 7234 identifies a minimum of 25 degrees. So that would have given us some additional bandwidth to potentially prevent some of those trips. So this is an example where if we would have had the settings set to be compliant with IEEE 2800, we may have avoided some of the lost megawatts during that trip. Some other things just to note: current blocking is not allowed post-disturbance as well in that section. And in general, IBRs need to be hardened or increase resilience to ride through these types of disturbances. I do encourage, right, and this one's a little bit of a different situation, but if the requirement's 25, but your equipment can do 45, sometimes you want to go ahead and utilize that additional equipment capability. Don't just go for the bare minimum if it increases the resilience. Now, if you set it too high and it's going to cause some equipment concerns or there's some impact to the system, I mean, those things have to be taken into consideration. But I just want to point out, one of the lessons learned we've had is if you're given a requirement, you're just going to park your relays right above it. And in general, resilience should be the principle rather than just compliance right above a particular set point. Finally, AC overvoltage is another example. We had one plant that had inverters tripped totaling 295 megawatts. The inverters tripped in about 1 to 3 milliseconds when the voltage exceeded 1.25 per unit. So when we look at the POI, the voltage was well within the ride-through range. Obviously, as probably mentioned in other presentations, the terminal voltage can be quite higher than what's at the POI, and that's where the rule is. You have to be able to ride through, so you have to account for any voltage rise between the point of interconnection and the inverter terminals. And when we looked at this particular scenario, the inverter terminal voltage was 1.3 per unit. On the high side of the main power transformer, 1.056 per unit. So we see a pretty big delta. And while Urcot already does have, a performance requirement to ride through, the transient overvoltage ride-through requirements that are identified in Section 723 of IEEE 2800, well, they're more transparent. So additionally, you're going to have testing, you're going to have simulation that verifies you're going to be able to handle that. If the plant equipment was designed and configured to meet that particular section, the AC overvoltage trips should be significantly reduced, if not removed altogether. So these are just a couple of real-life use cases where IEEE 2800, if adopted, and if designed and field verified and tested and modeled and everything else that comes along with that is done properly, we should see a benefit to reliability. So I'll stop there. I'll be hanging around to answer any questions in a bit.
Thank you, Stephen. And we'll come to questions after Brad shares his thoughts. So the next speaker, Brad Markowski. One day I will learn to pronounce his last name correctly. Sorry,
one day, Manish, one day.
One day. So Brad is with ISO New England, and just like Urcot, they are also exploring adoption of IEEE 2800. With that said, Brad, stage is yours.
Thanks, Manish. So hi, everyone. Thanks for the opportunity to present here today. I'm Brad Markowski. I'm a senior engineer in the transmission service studies group at ISO New England. My discussion is going to be fairly quick here. I'm leading the group implementing 2800 at ISO New England. I'm really here just to give an update on ISO New England's approach to implementing 2800. So our plan here is to use IEEE 2800 to develop a minimum performance specification for newly interconnecting inverter-based resources. So it'll be applicable to Type 3s, Type 4 turbines, battery energy storage systems, solar, VSC, HVDC, or really any converter-based resource. These minimum performance specifications will include the items within the standard that we feel support bulk system reliability, and we'll focus on the ones that are really critical for bulk system reliability. These are specifications and capabilities relating to things like ride-through requirements for RMS and instantaneous voltage excursions and frequency excursions, plant responses to disturbances, like active and reactive power control, protective functions like roll-off, momentary cessation, and some other, capabilities, possibly like fast frequency response or power factor capability. So, we sort of kicked off the effort officially back in April. This is kind of our timeline here, and I'll jump back to this slide in a second. But yeah, we started it back in April when the standard was published, and we made some initial decisions on our approach. At the time, we didn't really feel as though the standard was ready to be wholesale adopted as is, especially since there was no testing or verification standard to show compliance with 2800, similar to the conversations that were happening earlier today. So our approach really is to go through clause by clause and adopt the items, again, that are most important for bulk reliability, and make decisions on the settings as needed. We're going to take all these decisions and settings and the functionality that we want to be included and the capabilities we want included. We're going to put it into a strawman document, and that's not to say that we won't wholesale adopt 2800 at a later time, but probably not until the industry has more experience with 2800, and most likely after IEEE 2800.2 is published and widely adopted. So, once we have all the clauses adopted in our strawman document, we'll look to take these updates to, we'll look to make the updates to our planning and operating procedures and guides. And that's really when they'll be sort of, final and newly interconnecting resources will have to follow them. And, for now, there's some discussion about the verification earlier. Our plan for verification and conformity assessment is really a kind of two-pronged approach. One, we're going to rely on the OEMs heavily and the best industry practice to show conformance with the standard on sort of the unit level, and similar to how Urcot is currently requiring validation reports to be submitted. And then we'll also be doing our own sort of conformity assessments, by doing requiring certain tests at commissioning. We'll be checking the models, right? All those sort of things. And, speaking of the models here, let me just kind of jump through the timeline here. So again, currently the plan is to have the team create a strawman document with all the performance specifications we're looking to adopt. And then we're going to be presenting that to our stakeholders. Between the 6 New England states, we have a number of stakeholders, including but not limited to generation owners, transmission owners, load representatives, consumer advocates, regulatory officials, and others. It's a lot of different stakeholders in the New England region. The region does have advisory groups that are already in place, and we think using those kind of as the vector for approval for the region is most appropriate. There's been some questions about opening up the development of the standard to the public, such as as Urcot has done through their IEEE2800. But our plan is really to kind of develop it in the house and then bring it to the stakeholders of the region. So as I said, once an internal team develops a straw man, we'd look for review by the stakeholders and aim to bring the updated planning and operating procedures for final approval before the end of this year. Something else to note here is that 2800 has a lot of correlation with the modeling. And so in a separate effort, we're also updating our modeling procedures. So, in order to implement 2800, there's really this whole sort of ecosystem of updates that need to be made because they all sort of feed into one another. And so there's multiple efforts going on in those different spaces to support this. Lastly, at the time of approval, we kind of expect a phase-in period for newly interconnecting resources. We wouldn't expect, that the second it's approved, that resources are able to meet it. So, we do expect to also implement a phase-in period for the specifications, but that hasn't been fully decided on yet. So that's pretty much everything I have for the ISO New England update on adoption of 2800. And yeah, looking forward to some questions.
Thank you, Brad. So before I let you go, and I think you already kind of mentioned this, but maybe if you have to summarize again in a couple of statements, what are some major barriers that might lead to not adopt? I guess the answer is, well, we will adopt. It may be a piecemeal adoption till someday in future where it may be a full adoption. But anyway, I'll let you answer that. What are some major barriers that may lead to not adopt IEEE 2800?
I mean, the biggest part from the technical side, I think for us, is the fact that there's no way to specifically say that you are conformant with 2800, right? With 1547, there was the whole UL 1741 SB, and I think maybe there's an SD coming as well. Right, there was a specific testing standard for that, and you know, until that really is in place and widely adopted, I don't know how we get to a point where we say that you know, units and plants are certified and conformant and all these things. The other part here is the stakeholder support. That would be the other big barrier for us. We want to make sure that, you know, we're keeping the stakeholders of the region happy. And, you know, we do believe that IEEE 2800 does lead us to a way to more quickly and more reliably interconnect inverter-based resources, because, you know, Urcot is going to be implementing it, others are going to be implementing it, right? So if we all have the same sort of set of settings and standard requirements, then there really shouldn't be any of this, you know, well, I'm good in Urcot, but I'm not good in ISO, right?
Yeah. Stephen, do you have any thoughts on those, some major reasons or barriers that might lead to no adoption?
Yeah, I would just echo what Bradley just said. I think we're very much in a similar place where when we started presenting this internal to Urcot, I think a lot of subject matter experts had concerns about how do you validate, how do you make sure. We didn't want to just put out a meaningless set of capability requirements, but we are wanting to signal, you know, developers, and we are wanting to signal everybody, hey, we are going down this route. So go ahead and plan that way. We're working out the details as we go. So I think that's really, we got to get it right, or else we're just going to be pushing, you know, a bunch of words that are not verifiable, as Bradley was mentioning. We did have one legal concern about, you know, requiring adherence to a standard that an entity has to pay to access. You know, I'm having to run that down, but that's the only other, I think, legal barrier that has come up a little bit in our discussions that we have to work through. Besides that, you know, we're still looking at it like, can we structure this in a way, but we don't want to put all of our eggs in that basket. We want to go ahead and work the piecemeal in parallel so that we're making sure we get the progress we need.
Right. Thank you. And I think that that's kind of similar to, you know, what we heard from OEMs also. Well, in absence of 2800.2, how would you self-certify for all requirements? Some could be done easily than others. So Andy Hoke is the chair of .2 working group. Andy, this is more motivation for you that, you know, for easy and quick adoption across the industry, it's very important we get .2 done as quickly as possible. Helps both sides of the fence, right? The transmission and the developers and OEMs. So to the next question, is there some way to know which ISOs or organizations have adopted and which ones haven't? I'll go ahead and try to answer this. I don't think that there is an entity out there that I'm aware of has adopted this completely yet. I work for Southern Company, I mentioned earlier. We have a small team, just like how Brad mentioned, Stephen mentioned. We are looking into it, trying to revise our interconnection requirements. I was exchanging emails with someone at some other utility this morning, actually, and it was about adoption of 2800. So I think everyone is thinking about this. It may take us a little time to get to adoption, either piecemeal or full. But the industry is paying attention to it. There are a couple of other questions that are related to FERC. The first one says, how long should it take for FERC to adopt IEEE 2800? And the second one's something like, should ISO RTOs move forward with 2800 implementation through modified GIAs? Or is it likely this efforts would be superseded by FERC? Look, I don't think anyone on this panel can really speak for FERC. Eddie Lim is a good friend. I call him, he's a FERC staff. I don't think Eddie speaks for FERC. So I don't think we can answer that question. I always think we need to do what is right, and hopefully that would be it for it. So more to come, I guess, on it. One more question. So maybe I'll go to Sid and then Samir. Does 2800, does adoption of 2800 significantly raise equipment cost? So Sid, if you're still with us, do you want to try to answer?
Yeah, so I'll try to answer it for two pieces of equipment. One is solar inverters and solar and battery storage inverters. And the other one would be for wind converters, especially type 3 wind converters. Now, like had been pointed out by Lucas, we've been evaluating the 2800 with a view to start putting elements of 2800 in new products. And in fact, we're aiming to do things across over time so that we would have something which is fully compliant, or inverters and wind converters compliant. Now, as far as the inverters, solar inverters and BESS inverters are concerned, there's a lot of concern, and I think it, in a different way, that's also a concern with this multiple write-through requirements and how that can be met in terms of what are the power supply requirements, et cetera, and whether that would significantly impact the cost. We still haven't gone through the whole design process to say that. On the other hand, on the wind side, there are certain requirements, and some of them may be providing VARs at zero power, and some of those kinds of things, which may impact the cooling systems, and that could impact costs. Again, we don't know that because we haven't gone through the whole design process, but there's some possibility of that for sure. And then the last thing I do want to point out on wind turbines, because it's not just the electrical portion, but also the mechanical coupling, that is being investigated as well, whether full compliance to 2800 has impact on any of the couplings or any other. So what would have to be done to meet those? So it's an ongoing process. Don't have a full answer at this point.
Right. And that's understandable. It's ongoing process. Samir, any quick thoughts on cost without really putting dollar numbers? Right.
No, Nes, I agree with Sid. There would definitely be cost implication, and we're certain of that, especially for some of the stringent tests, like transient overvoltage requirement. Like I mentioned in one of the presentation, we are also grasping how can we test those when the requirement is so shorter than the response time of the turbine, and also multiple dips. How do we test that? And those kind of requirement, not only like Sid mentioned, unlike solar or battery inverter, we have to take the whole thing to the field. It's a whole turbine testing, not the converter testing. Yeah, I mean, definitely cost implication will be there, and more than cost, I would say the time. Like Alex pointed out, there are only few facilities in the world that can accommodate the whole turbine, the prototype turbine, right? and you have to find a time, you have to time manpower, you need to have a good wind condition and all that, and all that thing. So I think we're more contingent than time as well, and cost, and definitely there will be cost implication because of all that.
Right, right. Good deal. And I think when we were developing 2800, you know, it's IEEE standard. We don't really talk about cost in dollars, but we understood that maybe this is going to raise cost some. But as far as the requirements apply to all OEMs, then really it's not really a competition issue. Maybe we get a better equipment, a little more costly, but it's essential for grid reliability as we move, forward with more and more renewables on the grid. That is actually one of the slides I use whenever I get a chance to outreach. We talked about capability while thinking about the future grid. Now nobody knows what future grid needs, but we scratched our head as much as possible and try to find a balance between a Ferrari and a horse carriage, if you all remember that slide. But anyhow, hopefully it's not a deal breaker. I'll try to answer this next question. I think Jason alluded to this in a very first presentation as we kicked off. Someone asked, please go over the NOPR. I believe they're talking about the interconnection reform NOPR versus IEEE 2800 conflict, since the comments are due next week. So very quickly, the NOPR, and this is just one paragraph out of many hundreds of pages. It says for abnormal voltage conditions within the no-trip zone defined by NERC reliability standard PRC 024-3 or a successor standard, maintain power production at pre-disturbance level. Unless you need to change the output for frequency response. And then it goes on to say that maintain generator facilities voltage schedule. Provide dynamic reactive power to maintain voltage schedule. I think what Jason was trying to convey is that when you have a very abnormal voltage, 50%, 40%, when you actually a fault condition, or maybe a system disturbance where the voltage has depressed significantly below nominal, then these are current limited devices. And it's best that the active power is reduced and reactive power or current is increased so that the voltage is restored. And then we restore active power back to pre-disturbance level as quickly as possible. We call this a reactive current priority in IEEE 2800. And even before 2800, this concept of reactive current priority had existed in various NERC reliability guidelines as well. So I think that's the conflict. I think the decision to operate in an active power or current priority mode or reactive current priority mode should be based on system studies. Right. So my comment would be that let this be decided based on transmission planning studies on how your system behaves, what is needed. Now, even when inverters operate in a reactive current priority mode, how much active power is reduced to prioritize reactive current is configurable by a control gain settings. So there is a room to find a balance. It's not that reactive current priority means zero active power. There is a way to find a balance. But anyway, all those things should be determined based on system studies and need of the systems as the grid evolves. Let's see if we have maybe 1 or 2 more minutes left. Let me see if there is any other interesting question. For ISOs, so maybe Stephen and Brad again, regarding your concerns on adopting 2800 before DOT2 is published, how do you currently verify that your interconnection requirements are met? Brad, I'll start with you.
Sure. So, we have our interconnection requirements listed, obviously, in the, the LGIA and SGIA. And we do a lot of model acceptance testing. And, the models, before the plant obviously comes into service, it's all checking the models, checking the data that's submitted, making sure that it all conforms with our requirements. And then once the plant gets to the point where they're syncing with the system, then we do require them to give us some commissioning data as well, to make sure, say, they meet the droop requirement and that their AVR is functioning, in the way that the models had predicted. So there's a number of different steps that we take, along the entire timeline of the interconnection.
Thank you, Brad. Stephen, thoughts on that question?
Yeah, once again, very similar to what Bradley laid out. I would just point out that, the model verification testing that we do is dependent on the model we receive. And so if that model is not proper or doesn't capture some of the inherent, settings at the very detailed level for ride-through, it may show that it's okay, but then reality isn't. Likewise, we do have as we get close to synchronization, a verification that the model, meets the field. But once again, we're dependent on information that's being provided to us. And so there is some verification, but there is some trust in that. And I think sometimes in real world, we're seeing opportunities where the models don't exactly reflect real world behavior. And we're also seeing where it was supposed to be set a certain way and it's not. And so there's definitely opportunities for improvement beyond that. We do a battery of frequency and reactive tests as well. But, a lot of that is a little bit more steady state and not in a ride-through mode type thing. We do have some pretty advanced tests, so we've been ahead of the curve a little bit and putting some of these other tests out there, like high voltage ride-through and phase angle jump, but it's very dependent on the models.
Thank you, Stephen. So in respect of time, I think we'll have to wrap up this session here. Let me say thank you to everyone for sharing their thoughts. Thanks to all who asked questions, made this a more interactive session. As you heard from both sides, 2800 is published, but adoption remains to be seen how it works out. We hope that, the dialogue between two sides of a fence, the transmission, the developer, and the OEMs will continue, and we'll learn from this. And in the long run, this is a right step or a step in the right direction. With that said, let's take a short break now. We'll reconvene at 2:50 Eastern Time, 2:50 p.m. Eastern Time. Thanks for joining us. Thank you. And
welcome back to our workshop. It's my honor to moderate session 6 of this workshop. My name is Mark Ahlstrom. I'm the president of the ESIG Board of Directors and vice president of Renewable Energy Policy for NextEra Energy Resources. The U.S. Department of Energy provides vital research and support both to industry and for society at large. And today we're going to focus, in keeping with our topics here this week around the interconnection process, on the very important Department of Energy I2X initiative. We're going to be hearing from Cynthia Bothwell. Initially, she is the Grid Integration Engineer for Systems Integration. Cynthia is with the Wind Energy Technology Offices at the U.S. Department of Energy. She'll then be joined by Tom McDermott, who is Chief Engineer and Solar Subsection Lead for Pacific Northwest National Lab. We will have time for questions, and for this, we're going to continue to use the Slido.com platform. So please go to Slido.com, enter the event code of ESIG11 to ask your questions and to vote on the questions that are there. And we'll use that to prioritize a discussion with Cynthia and Tom after the end of their presentations. So with that, Cynthia, will you start off with the overview and tell us about I2X?
Will do. Thanks a lot, Mark. And we really appreciate the opportunity that ESIG has provided us to kind of discuss our program and hopefully get some feedback from this audience. And so this is going to be a lot less technical session and maybe make you think about some of the other issues around interconnection and how we can solve them and prioritize them. So I'm going to first go over just kind of the background of interconnection, which you all know a lot about, but sometimes maybe you think about your one particular technical area and don't think about the interconnections of that area with the process as a whole. So I'm just going to kind of step back, give the big picture and talk about that. And then I'm going to talk about part of the I2X program and some of its pillars, leaving out one important one, which is our roadmap development, which I'm going to transition to Tom McDermott, and he'll discuss that. And then we have some audience input sessions. So it's not just about asking us questions, it's about us trying to elicit some feedback from you to make this program more productive. So I know, technical audiences know a lot about interconnection, and you've thought about how this impacts your utility or development. And the developers, maybe more than the utility engineers, think about all the laws and the processes and all the hoops you have to go through. But I'm a utility person by background, and sometimes I just get stuck in my little niche and didn't think about all the interconnections, all the processes that the developers have to go through too. And I think we had some really good examples on day one of this workshop of how those kind of chicken and egg problems that come on with the developers and the engineers and the interconnection process. So thinking about these complexities, I want to put this a little bit, the problem, the scale of the problem, and you see it ever increasing and getting ever more difficult. But the Biden administration's current goals kind of represent this. The Wind Office has this rap song they've developed that's 5 times by 35. And so that's only 13 years from now, we're going to have 5 times as much wind on the system as we have today. That's huge. So wind started back in the maybe 1940s, very small scale. Maybe in the 1980s, it gained a little more traction for small utility, municipal purposes. So from the 80s to today, about 40 years, we grew the wind program, and now in the next 13 years we want to 5 times that. So again, a huge problem of scale, and this is all to meet the zero carbon futures. We may be also changing our load and the nature, so all the load profiles that we've had for years and years don't apply, and so everything's changing. We're relying on the weather, and weather might be changing. And we're considering more and more how equity factors into this equation, and how we can provide a good transition for that includes consideration for everyone. Okay, so some of you are familiar, probably all of you are familiar with parts of this interconnection process. And I just want to show it because we're going to talk about it in context with some of the solutions that go along with this. So the orange in this slide is representing the distribution side of an interconnection process, while the teal color is more of the transmission generator interconnection process. And you go through all these phases, but think about too, some projects don't fit neatly into one of these or the other, such as a community solar installation, or the new FERC 2222, where there's aggregation of distributed energy resources. And they might have to follow both lines because they have impacts on the local distribution system as well as maybe broader impacts on the transmission system. So navigating this could be very complex. So just a little history. Back a year ago or so, we held in the solar office, mostly the solar office, we just helped, held a workshop, and they did it in a series of two components. One, they had a group of developers get together so they could figure out issues most important to developers. And then they had a group of utilities get together and figure out the issues most pertinent to the utilities. And of course, both parties complained about the other, right? And that's just how it is. So, but we need to come to solutions, and we all have to come to some common ground. A lot of these issues that were taught in this workshop, ESIG's already trying to, has had some workshops already at this workshop and earlier webinars to address some of these issues. And so part of what DOE wants to do is encourage more of this. You know, how can we get all these parties together thinking about the complexity of issues, finding common ground and solving those problems. But some of these issues haven't been resolved yet. So I know there's been a lot of good discussion on transmission planning, but the intermittent impacts on reliability. But what about these T&D coordination impacts? I still haven't heard a lot going on around that issue. In administration, we've talked about, you know, how to make maybe models better, how to train people up to get the right tools so that we can get these things faster. We've talked a little bit about transparency of data and models, but that's still a big issue, getting to that transparency, especially up on the transmission system where there could be, you know, confidential data for really good reasons. And then the market rules, we know that FERC is doing a lot in this area, but there's still going to be some gaps. And so we're still looking to figure out how we can address some of those gaps. So that was a year ago. Just a couple weeks ago, we held the solar group again, held a workshop with the National Community Solar Partnership. And many of the issues came out to be the same thing. This lack of transparency of data. You know, maybe they wouldn't speculate and so much on siting if they knew ahead of time which siting was going to be more favorable from an interconnection cost basis, and just a whole host of issues that come down to kind of being the same. And their issues were focused on those beginning stages of development, the siting, the interconnection process application, and then understanding the results of the interconnection studies. But all those parts are integrated together. So we went and kind of plugged in some of the problems and potential solutions with all of the steps in the interconnection process. And this is kind of just our first cut at doing this, and Tom will talk a little bit more about the roadmap that will kind of look at all these areas and how they fit together and solutions. But we're also here today to get your input. So you can also use the Slido tool to send us comments, send us feedback. What's important to you, and what should we change? And I know Tom's going to be walking you through some guided question and answers too, where you can give us feedback. But we're here to take that feedback today on your priorities and your areas that you can't solve. It looks like developers feel better once they get that interconnection agreement and everything comes back in their lap and they can work, they can manage everything. But these, when the process is kind of out of their control, that's when it's more problematic. Okay, so again, just to give you a little bit about the scale of the problem, I'm showing the the existing capacity that was in 2010 and then 2021. So we're starting to see this small shift or transformation to more renewable weather dependent resources. But then look in the queue in 2010 was tiny compared to the queue today or last year, and notice that the capacity in the queue as of 2021 was higher than all the capacity installed on the system throughout time that was in service. So again, we're talking about huge amounts of generation contemplating getting installed on the grid. And then the map on the right kind of shows where that is in different locations throughout the United States. So what's DOE thinking about this? Well, I don't like reading slides, but I'll read you the kind of this mission because it's really important. We want to enable simpler, faster, and fairer interconnections of solar and wind energy resources while boosting or at least maintaining reliability, resiliency, and security. So we want it all, not just, we don't want just the renewables on the system. We need to make sure that system is reliable and secure as well. So we've developed, based on the stakeholder input we've had so far, these 4 pillars that we feel are important foundation for this program. And I'll be going through 3 of these pillars: the stakeholder engagement, data collection, and technical assistance. And Tom will be talking about the strategic roadmap, and he might also be talking a little bit about technical assistance and stakeholder engagement from his perspective. Okay, so stakeholders, we're looking across the board, not just the developers and the utilities, but also the governmental agencies that are kind of motivating certain types of generation or clean energy or load shifting activities onto the system. We're looking at trade groups, environmental groups, others that are participants to this process, you know, maybe from the side, but it still impacts them as well. So we're trying to be all inclusive in this stakeholder development. And we've created a platform. Many of you may have already be participating in this, but our vision is to set this up into different working groups, cross-secting different segments. So regionally, where issues might be different, by sector, where you may be able to share best practices of how to do something between your utility or the developers or some governmental regulators. And then by topic, so we just heard about standards adoption of 2800. So we hope to have a working group on that. We have another one on 1547. We have one on energy justice. And we'll continue to build this platform and develop the working groups to meet your needs as the stakeholders to this process. Okay. So moving on to the data collection and transparency. Some of you may have heard Joe Rand from Berkeley Labs speak, I think it was back at the end of May, on some of the interconnection data they've been collecting and reporting on. And this has been useful in the FERC NOPR process, but also to utilities and developers in different areas, and for us in developing the program goals. So we want to do more of this, and we want to do stuff that's meaningful. And so I was looking at this particular graph, and it talks about the timing from the time of the interconnection request to commercial operation. Well, this doesn't necessarily tell all the picture because different projects take longer to actually construct. So one of the things as well, we want to change the metric from time of application to the time that the interconnection agreement is completed, and then that seems like more that's in control of that interconnection process, and then less on, you know, whether it takes a short time for a developer to develop. And each technology, of course, has different timescales for how long it takes to develop. But you can still see some trends that places like California, where there's very high penetration of renewables, have longer times, increasingly longer times, and places like New England that previously had less renewable development had shorter times. So maybe there's a connection between penetration. So this two-dimensional look, again, doesn't tell the whole story. And one of the parts we want to increase is how can we dissect this data differently and understand it better. We also have gaps on the distribution side, just collecting the data for community solar projects, for distribution projects. How can we collect that data? We're hoping that you might participate and help give us data and figure out how to do that in a manner that preserves your confidentiality. A few more examples. Again, another two-dimensional look at the interconnection process by renewable type. And again, here we're seeing higher times for wind. But what we don't know from this two-dimensional look is whether, you know, do those peaks correspond with when new incentives were released or incentives were about to expire, and that motivated people to quickly enter a lot of projects into the queue? Is it because when penetration's higher than other penetrations of projects? You know, why? So we've collected some data, but now we need to kind of understand what it means and how to take that and improve the process. Other thing, so that's kind of included in some of these comments I put up on the side. Okay, another pillar to the I2X program is to provide technical assistance. So this can come in many ways, and here I've listed 4 that we've kind of brainstormed and thought about. We don't all, you know, again, making that process fairer, we don't have all access to the same resources. So I mentioned I worked at a utility. If you work at a big utility, I worked across big and small utilities. When you work in a big utility, you might have somebody dedicated to a certain process or outcome, like interconnection, shepherding interconnections or doing the studies. But if you work for an electric co-op, a distribution co-op, you might be wearing 20 different hats. And interconnection is one of those that you have to do. And then how do you manage that and understand that you don't have the time to, you know, really understand that. So we want to try to help fill gaps in understanding and bring everybody up so they can effectively process interconnection requests in the best manner possible. Again, so these are just a few examples of that. Here's our timeline. We kind of did some pre-work in 2021, surveying the audience, the stakeholders. Then we finally got some money in 2022, so we got really serious about putting together this whole process. We kicked it off a few months ago. In the second quarter, we had a big webinar launch event, and we kicked off our website platform. And so now we're kind of in this building this roadmap. And again, we're hoping to get your input and doing as many stakeholder engagement activities as we can. We started some technical assistance. We're doing some office hours, and maybe Tom will go into that more, but that's where you can, on an individual basis, personal or corporate, sign up for an office hour and get kind of us to talk to you and kind of help point you in the right direction for some resources and so forth. And then hopefully by the end of the year, we have a great roadmap to tell us what are the important areas, what can DOE do with its partners, and what can industry do, kind of segmenting out the roadmap of where important activities need to take place. And then the next 4 years, executing that roadmap through a bunch of activities. So what can you do? Well, here's our website platform that you can go to and find out more. We encourage you to join this group. You can observe what's going on, and we would really, again, hope that you can help us understand the process more through data or comments and whatever. And then you can participate through the forums that are going to be launched soon on that platform, or signing up for office hours. We already have, and this is old news, I'm sure, because our partnership group is growing every day. But as of last week, we had about 570 individual partners representing 380 different organizations. And last but not least, here's our team. The top row is the ones spending the most amount of time on the project, but the whole team is very important to supporting this. So some familiar faces you might see from the solar office, and Gian, I know, has been involved in ESIG and activities from our wind office. And then from the National Lab, Tom McDermott will be speaking shortly, and Joe Rand and David Narang from NREL. So those 3 labs are our top team partners at this time, but we are seeking, as we see the need and as the roadmap indicates, additional partners. Within DOE, we've been talking with the Office of Electricity and the Water Office and the Vehicles Office and the Fuel Cells, Hydrogen Fuel Cells Technologies Office, as they all play a part in this process as well. So this team that I'm showing you here has hundreds of years of experience, and we hope to help this whole community that's cares about interconnection to make improvements. So Tom, I'm going to kick it over to you now to deep dive the roadmap.
Okay, thank you, Cynthia, and I'd like to thank Julia and Charlie and Ryan Willis and everybody else who offered us this opportunity at the last minute. Like Cynthia mentioned, we are hoping to gather feedback as we kick off this strategic roadmap effort. Okay, the guideline is approximately 5 years, and we have a simply stated goal of a 50% cost and 50% schedule reduction in 5 years. Now, in the fine print, we would add that this is to be done without impacting grid reliability and resilience in a negative way. But that's like any engineering problem, you have constraints, and so our goal, our focus is in the cost and the schedule and the fairness, but without harming grid reliability. So we need some expert feedback on what the goals should be, and that's our goal here. Setting milestones along the way, figuring out key performance indicators and metrics to know how we're doing. Transition planning for the new processes is important, and you know, the buy-in especially. So the 50% cost and schedule is a very simple goal, but it needs to be customized, we think, for different sizes and regions, and transmission versus distribution, for example. So we're starting to outline the roadmap, and we're aiming to have a first draft due in March, in about 6 or 7 months. So the team that Cynthia mentioned includes 3 national labs and 2 offices at DOE. We meet every week to try and coordinate progress towards this goal. So we have a rough outline established. We're assuming that the FERC NOPR is going to be, they're going to issue some rules, and that's going to be the baseline. So, for example, cluster studies is going to be the preferred or required means of handling the bulk power system queue. We wanted to discuss the roadmap's goal of 50%. New data collection efforts, sprint studies, I'll say more about that later, but we want to have some room for experimentation. We don't necessarily think that 2022 changes are going to solve the whole problem for the next couple of decades. Help states and other agencies, entities adopt new standards and identify gaps that aren't addressed right now, or things that we know that are in flight. Also, the interconnection study guidelines, these are separate documents. They're part of the roadmap, but they will be referenced by the roadmap. So I'll say a little bit more about that later. But Ryan, if you would show the first Slido poll, we want to ask some questions about whether the 50% goal is appropriate and how that would be modified for different scenarios. So let's see, Ryan, is that up yet?
Yes, it's in WebEx, so folks are starting to fill it out right now.
Okay, cool. So I want to say I was looking at the Slido questions, and while people are filling that out, somebody asked about how does DOE propose to handle the mutual exclusivity of the goals, faster and cheaper, yet reliable, resilient. So we do want to maintain the reliability and resilience at least as good as it is today. So that's a constraint on how we achieve faster and cheaper. I don't know about the rap song that Cynthia referenced. The next question is, inverters can't support frequency and voltage at the same time. You do have real power priority or reactive power priority, but depending on the inverter capabilities and the control system capabilities, you can actually attempt to control frequency and voltage at the same time. Rotating machines do this, for example. So there are often trade-offs and constraints in the control system design, but we don't see those as mutually exclusive. And the other questions about the investment tax credit and the funding opportunities, I don't think we can address today. There was a question about what energy justice means. So I have a link in one of the subsequent slides that has a pretty good background, but in words, it's the idea of sharing the benefits and burdens of this transition to new renewable energy, for example, in production and consumption, but to spread those benefits and burdens equally among different segments of the population and communities. So it is a fairness goal, but it's also, we see or can observe that when these goals are not met, it's a barrier to adoption. If you're not meeting energy justice goals, then there's resistance to new wind plants, new solar plants. If people don't see that they're benefiting, why should they support it? So that's one way of viewing the importance of that topic. Okay, Ryan, should we move on?
Sure, let's give folks maybe another 20 seconds just to wrap up their last question, and then I'll close the poll.
Okay, thank you. So these results, we're going to send those out to the attendees. We're not going to show them live right now, and I'll explain why in the next poll. But we will use this information, and we will even follow up when that's warranted. Okay. Moving on, that's the roadmap outline. So this graphic expands on what Cynthia was talking about with the data collection efforts. So we have some existing mechanisms. SolarTrace NREL, one of our partner labs on this, collects information on permitting and applications in the state of the queue up to 50 kilowatts, but really in most cases up to 20 kilowatts, and it's a voluntary mechanism, so it's not uniformly covering the nation. And then Berkeley Lab has a website and a report that a lot of people track called Queued Up, and they're looking at the bulk system interconnection status based on data that FERC requires to be reported. We know there are gaps in some size, 50 kilowatts to 50 megawatts, and it may be wider than that. Some of the information on energy equity is tracked in census tracts. So the LEAD tool, if you're not familiar with that, it's a low-income energy affordability data tool. And so what we want to get at is how are community solar projects, for example, benefiting different segments of the population. Some of that information already available is geographically based. So in a data hub, we want to link all that up to define both metrics to gauge our progress according to the roadmap, and also provide a public portal to access to by other stakeholders to the data that we're collecting. So two purposes of the data collection: for public use and also our own metrics. Okay, we're also using with public data and tools something called sprint studies. And so these are short, 3 to 6 month efforts. We want to look at, say, improvements to the queue process. Say we want to do better cluster studies, or say we want to do an alternative to the queue. So we simulate applications of wind or solar power, social factors. We're using publicly available grid models and using existing simulation tools. And you have an analyst in the lower right corner trying to use the tools and the metrics that are available to achieve their objectives, which is maybe connecting new renewable energy projects or new storage to the grid. So we can we think of simulating this process, running a little experiment in a sandbox to see how different alternatives to the queue might work. So we have 4 public test systems identified. For transmission on the left, there's the 240 bus WEC model that NREL has added inverter-based resources to it. And more representative of the Midwest, the 118 bus system. It's an old AEP model from the early 60s, but really been enhanced with more data and inverter-based resources as well. And those are publicly available. And the advantage of those is that when we write these sprint study reports, others can look at the assumptions that were made and maybe look at alternatives and replicate the results. And then on the distribution side, we have 2 fairly large IEEE test feeders, so 9500 node, which is based on the 8500 node model, but it's enhanced with more DER and a couple more substations, so it can operate in alternative ties or islanded mode. And then the low voltage network, also publicly available, representative of urban distribution systems. And so the idea is that we would run simulated queues, and this is an example of a place where other parties, other utilities, consultants, developers may want to participate in these experiments. And the next slide. Oops, sorry, too many. And so those public systems are also going to be used in the technical guides to interconnection studies. And we think there'll be 2 separate guides, one for bulk power systems and one for distribution. Although there are a lot of common elements between them, you have to set the assumptions, criteria, decide which standards and guidelines are going to apply, collect data. Advanced tools, a lot of times, I use personally electromagnetic transient tools a lot. They can be used on bulk power systems or distribution systems in certain situations and so on. There are some different elements which I've highlighted in yellow. That's what the yellow highlighting means. So on the distribution side, you have hosting capacity studies, impact studies, influence of consumer-owned storage and vehicle chargers. Over on the transmission side, you have cluster studies, which are going to be required. The restudy criteria would get special attention. Post-commissioning models. Some of these you could argue are just as important on distribution, but there are different degrees of emphasis and assumptions that go into it. And so that's why we think they're going to be separate guides. And DER aggregation is of special interest on the bulk power system studies. And both of them, you need a common report format so that people can understand the results and compare, studies from one project to another, one utility to another even. So we are ready for another poll about the study outline. So Ryan, could you put that one up? So the first one is a short answer, what was missing or wrong on the top level outlines. And so while you're thinking about that, I want to explain question number 2. And this is why we're not showing the results live. One of our ideas is to have an interconnection boot camp. So it's kind of like the operating and maintenance users group that ESIG has, that they have breakout sessions, people using different products, different vendors' products. And so if you're doing interconnection studies, you should recognize most of those tools, or maybe you don't, but you can Google them later. And so our thought is that we would have a hands-on workshop, so kind of like an interconnection workshop like this is, but hands-on using tools in private breakout rooms. And another thought is that we could have subgroups in our users group or working group on interconnection studies. We might have a special emphasis group on dynamics using some of those tools listed there. So we're just, what we'd use this information for is to go to some of those vendors and say, 100 people would be interested in using your tool in an interconnection workshop. Wouldn't you like to participate? So we're not going to publicize this, at least not directly, but we're going to use it. We think it's valuable information in planning our improvements in interconnection studies and best practices. Some of the tools you may not have heard of, I'd encourage you to check into those, but we think there does need to be some evolution in the tool capabilities and especially how they're used. The first question, of course, anything that comes to your mind, let us know. Do you think it should be one guide with appendices, or how do you think it should be structured? What's easiest for you to use?
Okay, I'm going to give folks 20 more seconds and then we'll close the poll.
Okay, the poll has ended. So we'll go on to talk about the sprint studies. So this is a way to bring some analytics into the roadmap. We don't want to just sit and think up new ideas and then write about them and try and persuade the reader that these are good ideas. We want to have some comparative analytics behind it. And so that came up with the idea of the sprint study. Sometimes when national labs do things, a study like this, they take a long time to produce answers. So these are shorter, more focused sprint studies, and on those public test systems, which are a medium scale, but still carry some important features of, say, the Western Interconnection or the Midwest, so that they offer some credibility of results and also allow us to complete the sprint study in a 3 to 6 month time period. So we have two basic ideas, and on the left we have the better queue. So we're going to assume that they're going to be clusters, as the FERC has expressed in the NOPR. That's a pretty strong hint that clusters studies are going to be required. But how to incorporate the new energy equity, energy justice metrics, how to address shared costs of system upgrades. So the cluster study doesn't completely resolve all those questions. Different ways of forming and managing clusters. How can you improve the process of building and validating a model? And how can you improve the tools and especially the restudies, how to make those more efficient? So incremental improvements in the queue. And then the other one would be something completely different, and our thinking so far is an auction-based process, which, if you recall, the communication spectrum for cell phones was auctioned off, and that worked pretty well. So we still want to incorporate new equity metrics, identify locations and quantities for new solar, wind, and we should add storage there, but new resources. Are we going to invest in renewable energy development zones, build transmission? And so there would be some investment in capacity there, and parties would have to bid for the right to build new resources there. So what are the requirements to participate, and what are the bid clearing mechanisms? So if you think about that, there are different processes, and there are ways that both sides get revenue, but there are trade-offs, and so our thought is to run an experimental, virtual experiment running both options, and to see what we learn and which of those is worth pursuing further. So that's the framework for the analytics. So you may be, if you're focused in on the queue and the cluster studies, you're probably more interested in the column on the left. But if you're interested in major changes or improvements, the auction process isn't set in stone, but we do want to look at alternatives to the queue. So it might be something different than auction, but we really want an alternative to the queue. And then the ability to adopt a standard. So I focused on IEEE2800. At the very bottom, National Renewable Energy Lab has a guide to updating interconnection rules. It's almost 60 pages long. And so I'd encourage you to look at that. It's for state regulatory commissions, but also municipal power companies, rural electric cooperatives, or any authority having the governance over interconnection rules. But once you adopt 1547, it's still some important choices left open. So there are disturbance categories, Roman numerals 1, 2, and 3. There are reactive power capabilities, A and B, and islanding time. It's still a preference for 2 seconds, but you can go to 5 seconds, and this is called conditional extended clearing time for islands. It's allowed in the standard. You can also have intentional islanding. And so there's a lot of choices in the standard, and you want to simplify that for people, entities considering adopting it. And so that's the idea of the gold, silver, bronze level. So they're not, you can actually make all these choices independently, but maybe there are scenarios where it could be simplified. The role of communications is important. What you're using it for, direct transfer trip, tends to be an expensive cost item for an interconnection study when it's required. There are some gaps, we think, in IEEE 1547 2018, and what happens if there's communication failure and the DER is relying on some central dispatch function for control of real and reactive power. What happens then? The utility right now chooses between 3 options: the SunSpec, Modbus, the IEEE 2030, which some people will say it's really IEC 61850. It isn't exactly, but it does incorporate the logical object model from IEC 61850, and then DNP3, which is of course now an IEEE standard. We want to get people, encourage them to look more realistically at islanding detection times, and when I say realistic, by probabilistic, so that you're not going to have a 0% probability of failure, but it's going to be some small number. And what do you do? How do you evaluate that? And edge cases that come up in the office hours that I think Cynthia mentioned. So if you go to that website, we do it every Friday afternoon Eastern time. You can schedule 20 minutes, and you can, if you don't like something you heard now, you can tell us about it. You have a question. We're happy to field those because it gives us a sense of the state of the interconnection process. And so one thing that came up in a recent office hours session is subtransmission, which is not precisely defined really anywhere that you can take from one utility to the next and realize, be confident you understand what subtransmission is. But it does affect somebody looking to connect DER, whether they're handled as subtransmission or distribution. How are those choices going to be made in the jurisdiction? Is it the regulator that's going to make that choice or constrain the choice, which can be left to the utility? And also the metrics. How do you gauge your performance? So in that link, the NREL guide, there is a discussion of collecting sub-process metrics, and we want to collect interconnection process metrics for DER. So we're especially interested in thoughts and mechanisms to address that gap, to know, are we really making a difference in improving the interconnection process? So energy equity, there are actually six aspects of it, and I won't read those. There are 6 factors, and there's some example metrics. And there's like a 30, 40-page report there at the bottom that gives you a primer on the topic and different ways of measuring it. So some of these can be quantified or maybe turned into equivalents for dollars, and some maybe cannot. But when you measure these outcomes across different populations, that's what we're getting at with the idea of equity. So at this point, we are ready for the third and last poll. Ryan, could you toss that up? So it's just, this may be a new topic to some of you, so just your first impressions. What's the most important or most applicable? What's the least applicable to your organization? And question 3 is a short answer. When you get that far, what are you missing in thinking about or addressing energy equity, as we've explained it so far?
Let's give it another 20 seconds.
Okay. So I think this is my last slide of substance, the project timeline. So we're in August 2022. We're writing up plans, documents that are eventually going to be published. So you'll see public versions of this, and they may be living documents as it's going to be a 5-year roadmap. We're starting technical assistance studies. Cynthia mentioned some of them. Another one, probably the first one we want to kick off from the labs, is how to collect data on that 50 kW to 5 megawatt size gap that there is in DER, and also how to start dealing with energy equity, but basically the data collection mechanisms. By March 2023, I mentioned this earlier, that we want to have the interconnection studies guides completed, the draft roadmap completed, and at that point, we're going to start presenting that in different venues and make revisions to it, get the new data sources in operation so that we have some initial metrics. We at least want to be able to baseline the status of interconnection as it is in 2023. And then we're going to have an external peer review. So this is an opportunity for you to get involved, that we will have a peer review of the sprint studies, which are the roadmap analytics and the roadmap itself, peer reviewed, and that we will have that published in June of 2023. And then September 2023, which is when this project ends, we will have a second round of technical assistance studies completed. So if you're interested in the technical assistance studies, you want help, we're really looking for multi-state leverage, where more than one state, if we're in the case of DER, wants to work together and solve a problem, and we're really focused on the interconnection process. The peer learning groups, I think we mentioned those, all these things before now, but if just go to that energy.gov/I2X website, you can see in the lower left of the slide, and that'll get you access to sign up forms and information for all of that. And once again, thank you. You're muted, Mark.
About that.
There you go.
Okay. Or somehow I got switched here. So I want to thank you, Tom. Thank you very much for this. I know you've already answered most of the questions, which helps keep us on time to move to Julia here. I think there's just a couple that came in. First of all, on the I to X meaning, that's what I saw at the bottom of your slide there, but maybe you want to clarify the acronym, which is a catchy little acronym. And then just briefly, there was a question also about just some clarification for some people about the 1547 adoption dates, if you see that one.
Yeah, I do. I do.
Okay.
Okay, so DOE really likes to come up with acronyms creatively, but the I2 is I squared, so interconnection innovation. That's two together, and then X is it's the second letter in the word exchange. So the exchange is in the project title because we want to get people exchanging information and ideas, and that's the reason for the office hours and the working groups and all these mechanisms that we're trying to build consensus. And it's also an extension. At least I read it. It's really trying to extend the interconnection process. So that's what it means, but it's an acronym that is supposed to be catchy.
Okay, great.
Hopefully it is. Can somebody help defining what the adoption date means? Okay, so the the standard was approved by IEEE and published in 2018, and I believe just now we're starting to get products seen in the field to comply with it. So this is 4 years later. So you don't see products appearing usually the day after the standard is adopted, and then beyond that, so part of it is the product maturity, and the other part is the jurisdiction that you're in. So a state, Pennsylvania, the state I used to live in, or Massachusetts, the state I live in now, each state will decide, when they're going to use IEEE 1547-2018, and often there has to be a regulation. So that's when it's ineffective in that state. And then, so the data manufacturer and the sync data, I'm not sure, but a lot of these, sometimes it's a hardware capability and sometimes it's a firmware version. So that's really up to the vendor whether the inverter complies. But yeah, the data manufacturer and the firmware date can be I'll be important. Let me
Thanks, Sam.
Right.
I think we'll cut it off there in the interest of time. I want to make sure we give Julia time, but thank you both, Cynthia and Tom, for this great presentation. And I do think you pointed out some interesting things, like kind of that sub-transmission gap here that kind of falls between some of the things we've talked about for this conference, between the bulk system and the distribution system and so forth. So appreciate the work and support from DOE, and thank you very much for your presentations today. I'm going to now turn it over to Julia. This whole workshop, if it isn't obvious, has really been Julia's undertaking here in pulling this together and putting together some amazing speakers. So I want her to have time to debrief us on her takeaways from this and next steps. So Julia, please go ahead.
Well, thank you very much, Mark, for such a nice handoff. Yeah, I would like to first, before I go into closing remarks, I would like to thank NAGF, NERC, EPRI for supporting this. I would like to thank all presenters who on such a short notice agreed to come and bring this very timely and informative material. And also to moderators. I think they've done an excellent job moderating discussions and Q&A and concluding every session. So just to conclude, I pulled highlights from every day and I'll quickly run through it to wrap up. And you can maybe read through some of the details later on as well. One thing to mention, we will address all unanswered questions and we'll post that on our event page. So just to go back to motivation for the joint workshop, interconnection queues have a lot of backed up generation there, and there are gaps that are being identified. FERC has issued an offer that is out there on improvements for generator interconnection. You just heard about I2X initiative. Heard about IEEE2800 and also about disturbance events that keep happening and we kind of need to address through some of these measures. So summarizing the first day, I think the key message is there is limited overlap between generation interconnection process and transmission planning process. In generator interconnection process, generator is being viewed as a cost to the grid, and that assumption basically defines the studies and how dispatch assumptions are being made and how solutions are being found. Whereas in transmission planning process, when new transmission upgrades are being evaluated, then benefits also are being assessed, not only costs. So there is a way to do it proactively, look at multiple benefits of transmission, look at generation, also having benefits to the grid by bringing cheaper and clean energy to the market, and also providing resource adequacy and resiliency benefits. So all of these benefits can be evaluated in the transmission planning exercise in a more consistent and fair manner. And so we need to move to the future where generation interconnection process and regional transmission planning are more integrated process. And so the benefits of integrating planning and generation interconnection processes is that you can consider generation needs over longer time frames. You can reduce scope of network upgrades that are triggered by generation interconnection, and then evaluate deeper upgrades through proactive transmission planning. that simultaneously considers multiple needs such as load growth and need for ensuring resource adequacy and resiliency and all those good things. The recommendation is to use proactive multi-value planning process to address both near and long-term needs, look beyond regional seams to identify more cost-effective interregional solutions. And it also removes uncertainty for developers for the affected system studies and costs that can be associated with that. Rely on advanced transmission technologies to address identified needs, and I think this is also highlighted in the NOPR. Improve and standardize study criteria and dispatch assumptions. So this is what we talked about on the first day, that study assumptions are not uniform across the U.S. And different transmission solutions are being identified because of that, and not necessarily all of these transmission solutions are the most optimal ones. And then utilize pragmatic cost allocation that roughly commensurates the benefits received. And one thing also I added here, kind of a highlight too, that the cost allocation doesn't need to dictate the design of the process, nor it needs to be a barrier to the process improvements. So if we find a cost-effective integrated generation interconnection and transmission planning methodology, the cost allocation can be developed then as an add-on to this method. And so a coordinated consolidated planning process task force in SPP and NL white paper offer some possible solutions how cost allocation can be done if generation interconnection and transmission planning processes are integrated. So I won't stop too much on this slide here. It just kind of lists out the benefits of proactive planning and also lists multiple benefits of transmission, so going beyond production cost savings. And so this is an issue even for transmission planning overall, not even talking about generation interconnection, that production cost saving is one of the main benefits that being looked at, but there are also other benefits of transmission, such as capital cost saving, emission benefits, risk mitigation, resource adequacy, and resiliency. So if all of these benefits are looked at together when evaluating transmission projects, then the economics of some of those projects can pan out better, and projects can be built sooner. So then on the second half of the day, we heard about different initiatives that are already going on kind of towards integrating generation interconnection and transmission planning. And so we heard about MISO and SPP's joint targeted interconnection queue study that shows that proactively studying large sets of generation and of generation interconnection requests, then the costs could be reduced and more optimized network upgrades identified. Then MISO LTRA was mentioned, and this is an effort that looks at long-term planning and looks at reliability, economic, and public policy needs for a diverse set of future scenarios. So it's proactive, it's scenario-based planning, and it looks at multiple benefits of transmission and identifies least regrets portfolio of transmission projects that are panning out across the wide range of scenarios. And so that 10 billion portfolio was identified that will support 53 gigawatt of generation interconnection and have massive cost saving. And then we heard from SPP on the consolidated planning process task force that recognizes interdependencies between generation interconnection and transmission planning and seeks to integrate these processes in, for more cost-effective and seamless approach. PJM offshore wind transmission study was mentioned where it's shown that proactively evaluating all existing state public policy, the transmission needs identified are 3.2 billion and can support more than 75 gigawatts of renewables compared to individual generation interconnection studies that are 6.4 billion of onshore upgrades and only support 15.5 gigawatts of renewables. So there are clear evidences of doing transmission planning and generation interconnection in a more integrated manner can save costs of transmission upgrades. And then Urcot generation interconnection process was mentioned as most effective in the US, and upgrades are focused only on local generation interconnection needs, and network constraints are managed through market dispatch, and then upgrades are assessed in the transmission planning exercise. Though it was pointed out that this transmission planning process is not sufficiently proactive and doesn't consider multiple value of transmission, and this is why kind of like identifying economic upgrades is a slow process. And then on the second day, we talked about studies and modeling, and here Ryan Quinn talked about multiple disturbances that have happened recently and NERC analyzed. So all of them identify need for more detailed, clear, harmonized interconnection requirements, better alignment of interconnection studies with project development timelines, accurate modeling, and we need models that reflect equipment and settings in the field and match actual equipment behavior. Models need to include controls, modes of operation, settings, and protection that could affect ability to ride through different disturbances, and also indicate provision of essential reliability services. We need to use right models for right study and studying right phenomena, and so we need all types of models in our toolkit. So talking about studies, we've heard from a developer, and it was an offshore developer who talked about that the developing project is a long timeline, and the project development faces a lot of uncertainty, so they can benefit from accurate transmission model data early on, and it reduces the uncertainty and project design iterations. For offshore projects, better coordination between grid operator and developer is needed to provide early indication on onshore equipment, because then they need to get associated permitting for that as well. And that may cause and may result in long development timelines. Interconnection studies should be timed in a way that allows obtaining more accurate models representative of equipment to be installed in the field, because information becomes available, further on into project development. And this reduces need for restudies and also increases fidelity and usefulness of the study results, because if you use models of actual equipment that will go in the field with actual settings that will be used there, and then the study is more useful. Stability impacts from projects coming online around the same time should be studied in concert, and using accurately parameterized models that reflect equipment to be installed in the field. So basically you need to study a common impact of all projects that are being built around the same time. And where relevant, for example, oscillatory behavior is being seen under weak grid conditions. In collaboration with OEMs and developers, control parameter tuning can be used as an alternative to transmission upgrades to save costs. And so we heard from Alice Shatak from Vestas talking about one of those cases where expensive transmission upgrade was avoided just by tuning control parameters at one plant. But this also can be done in a number of plants that are, say, coming in together in the same area, or there are existing inverter-based resources and new resources are coming. And so control parameter tuning is very helpful there. We talked about need for studies to be timed better for the time when more accurate models are available. I will not go in details here, but basically the proposal was to use more of screening study early in the process to provide some indication of costs and upgrades that will be needed, say, for thermal upgrades, but then time stability studies for later on in the process when there is more certainty about equipment and models that will be used. And I think in a FERC NOPR, there is also mention of first ready, first served, and there is discussion there about availability of equipment, so that will also provide more certainty about what equipment will be used and using right models for right studies. Then jumping on to modeling, basically it was pointed out that all models have their limitations, and generic models are not necessarily bad, and EMT models not necessarily means more accurate models, that all models need to be correctly parameterized, need to reflect equipment in the field to be a good model. Use appropriate type of models for appropriate studies. Detailed user-defined models are necessary for control tuning, while correctly parameterized, validated generic models may be used for planning studies. And then there are phenomena that are happening on the grid where you will need to use EMT study because this type of phenomena are just simply not captured in positive sequence. Control loop and protective functions relevant to studied phenomena should be included in the models, and that refers to any kind of model. Even if you have an EMT model that doesn't represent control loops and protective functions that are relevant, you will not see behavior that may actually happen on the grid. And I think today Steven talked to that as well. So what may in the Odessa event disturbance that was not reflected in the models, even EMT models. Model validation and diligent parameterization is crucial for any type of model. Limited validation is possible before and at commissioning, so unit type testing should be used for that, combined with careful plan design evaluation, and this can be used to gain fidelity in the models. And then post-commissioning disturbance monitoring can be used to provide more information and validate models for large signal disturbances as they happen. It's been identified that present models, both positive sequence and EMT, have been unable to capture some of the causes of inverter tripping that we've seen in NERC disturbance events. Limitation of models should not be confused with limitation of simulation domain itself, so we shouldn't just all now jump and do only EMT studies. Future models can be improved to include some of these behaviors, tripping behaviors that we've seen before, and this is relevant for both improving positive sequence and EMT domain models. And so these models need to capture things that we are seeing in the field and those behaviors. And so if included in the models and relevant tool is used for relevant phenomena, then we should be good and see these events in the studies as well. It is recommended to start collecting quality testing and validating EMT models ahead of EMT studies being needed. For example, ISO New England and Urcot have already been doing this for a number of years, and over time they improved the EMT skills and also model quality and model validation requirements. So it takes time to collect models, to validate models, to obtain skills in using EMT tools, and so it's too late to start collecting model when the study is needed. Day 3, probably in the interest of time, I won't stop too much on that. We talked about, because you all were in the day, I'm hoping we talked about IEEE2800 as a good harmonization effort. Similar effort has happened in Europe before, so it's not something new that haven't been done before. There is a benefit in having harmonized interconnection requirement across the boards, and it removes uncertainty for OEMs and for developers, and also improves reliability of the grid. We heard the discussion of OEMs, which was quite unique. I think it's first time OEMs actually talked about 2800 and the roadmap going forward. So majority of the capabilities that are outlined in 2800 are already there and available in existing equipment. Several more complex requirements will need to be implemented in new equipment, and we need to work on some kind of transitional arrangements to move forward before this happens. Plants may get built in near future that may not fully comply with 2800, and OEMs, developers, and grid operators should work together to realize those requirements that are possible to get online and then develop transitional arrangements for those requirements that are more challenging. Smaller developers, especially solar and battery storage plant developers, need additional education about interconnection requirements and performance expectations for inverter-based resources. So that was also identified. Also, grid operators need to be proactive to keep developers well informed on interconnection requirements, modeling requirements, and performance expectations. Some grid operators already started gap analysis of their requirements versus 2800 and also developing path forward with implementing those requirements. And the voltage write-through requirement proposed in FERC NOPR likely needs some revision to encourage IBR behavior that's more helpful for grid recovery. And harmonization with PRC 24 and IEEE 2800 language would be beneficial here. So you heard about I2X initiative last, so I will not go through this bullet points, but you can read it, once if you look at the slides again. So what's next? All presentation materials will be posted on the event page. The workshop was recorded and recordings will be made available on ESIG YouTube channel. I believe first 2 days are already there, and same goes for presentations. Ryan is posting this extra quickly this time. All unanswered questions will be addressed and we'll post them shortly, probably within a week time from now. ESIG will summarize highlights of the 3 days workshop in 3 blog posts, 1 for each day, and we'll send an email out to all workshop participants once we have done this, and that should be by the end of September. And ESIG will continue with webinars related to interconnection process, studies, modeling, and interconnection requirements to share best industry practices on these topics, inspire industry reforms. So with that, I would like to thank you all for participation and stay tuned for more information. Thank you all and goodbye.